Okay, in this next video, we're going to take a look at how to do Riemann sums. So it'll be the first portion of this review set, number 2. So first thing we're going to do in Riemann sums is most of the time they're going to be in tables, okay? So we're going to read the first part of the question. It says, the store tracks the sales of one of its popular board games over a 12-week period. The rate at which the games are being sold is modeled by the differentiable equation G, where G of T is measured in games per week, and your weeks go from 0 to 12. So, part A, it says approximate the value of G prime of 8 using the data table. So, 8 is located in between those 2 points. So, we're going to use G prime of 8, and we're going to find the slope between these 2 points. Because G prime means the slope. Okay, and this is going to be non-calculator, so you get 1,200 divided by 4, and you should get 300 games per week. Now, when you're doing units on this type of question, you always do your y units over your x units, okay? Now, next part is where we're going to get into the Riemann sums. So whenever I taught you how to do Riemann sums, we always did this. So we did 3, 3, 4, and 2, okay? Now, right-hand Riemann sums, we don't use the left point. So we're going to do 3 times 450 plus 3 times 900 plus 4 times 2100 plus 2 times 2400. Okay, and you should get 17,250 games. Okay, so this is the amount of games that are sold over a 12-week period. If we're interpreting the units. Okay, and then I added a part C to this question so we could go through and do the LRAM and the trapezoids. Okay, so your LRAM. Okay, so when we do LRAM, we're going to include the left point, but we're not going to do the right one. Okay, so it's going to be 3 times 160 and 3 times 450 and 4 times 900 and 2 times 2100. Okay, and you should get 9,630 games. Okay, and then trapezoids. So the area of a trapezoid is going to be 1/2 the height times b1 plus b2. So that's what we're going to do. So it's going to be 1/2. Your height is always your delta x, which is 3. And we're going to add the 2 bases together. So 160 plus 450. Repeat the process for the next. So we're going to do 450 plus 900 plus 1/2 times 4 times 900 plus 2100 plus 1/2 times 2 and 2100 plus 2400. Adding all those terms together, we should get 13,440 games. Okay, so as we continue through the next couple weeks, whether Riemann sums show up on a velocity problem or any sort of other problem, you should be able to do it rather easily. Okay, integration with geometry. So remember, the definition of an integral is the area under the curve. So what I would do in this case is I would go through and I would find the area of each of these sections. So if you look at this, that's a triangle. 2 times 1 is going to be 2, and then divided by 2, so that because the area of a triangle is 1/2 the base times the height. So this is going to be a -1. Now, you got a semicircle. Okay, so your semicircle is going to be a is equal to pi over 2r squared. Okay, so pi over 2. Your radius of this portion is going to be 2. So it's 2 pi. Now, since it's under the curve, this little section is going to be pi, and this little section is going to be pi, just in case we have to look at other portions of the graph. Say it's, split in 2. Okay, then the area of this triangle right here, 1, 2, 3, 4 by 2 is 8. Divide that by 2 is 4. Okay, now the integral from 0 to 2. Okay, so it's this area right here. It should be a -pi because it's under the curve. It's under the y-axis. So anytime it's under the y-axis, it's going to be negative. Part B, the integral from 2 to 6 is this area right here. It should be 4. Part C is going from -4 to 2. Okay, so it should be a -1 minus 2 pi. Okay, the area from -4 to 6 is, we're going to add all those together. So it should be 3 minus 2 pi. Okay, part E, we're going from -4 to 6, and it says absolute value. So when it's absolute value, we're going to make sure that we make the negatives positive. Okay, so it should be 5 plus 2 pi, because I make that a positive and make those positive also. Now, the last part. So what we're going to do on this one is we're going to split it into 2 separate integrals. -4 to 6 of f of x dx plus 2 dx, and I'm going to go from -4 to 6. Now, we already know what the answer to this portion is, because we did in part D. Okay, now let's integrate this. So the integral of 2 is 2x. Plugging in, you get 12 minus -8, which is equal to 20. Okay, now what we're going to do is we're going to combine the 3 minus 2 pi plus 20, and you should get 23 minus 2 pi. Okay, so I know we haven't seen this in a while, so that's how you use some basic geometry to evaluate the integral. Now, what I'm going to tell you is on the 2020 AP test that we're about to take, they're probably going to put something that looks like this on there. So that's why we're going to be spending a lot of time on this over the next few weeks. Okay, next example. So when I go to break this down, I know some of you like to use the boxes and count by boxes. Okay, so this is a 1 by 1. Okay, this is a triangle. So the base is 2, the height is 1. So 1/2 times 2 is 1. And this is a 1 by 2 triangle. So that area is also 1. So if I add them all together, the integral from 1 to 7 is going to be 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Now, on the next page, for some reason it kicked it to the next page. It says find the average value. So the average value I'm going to zoom out a little bit now. So the average value of this thing is going to be 1 over b minus a, so 7 minus 1, times the integral from 1 to 7 of f of x dx. Well, we already know what this is. It's 8, and 7 minus 1 is 6. If I want to simplify it, it comes out to be 4/3. Okay, and then we're going to go on to the next page, and let's do some second FTC questions real quick. Okay, so part A. So remember, on second FTC, we're going to be taking the derivative of an integral. When we take the derivative of an integral, saying that the variable x, is the top limit. It works like that every single time. So when I take a derivative of the integral, I plug in the top limit everywhere there's a t, and then I chain rule the top limit. So it's just sine of x over x. Part B. Same thing here. Top limit's x, I'm going to plug it in. So e to the negative x squared. And then I'm going to chain rule the top limit right there. So the derivative of x is just 1. Part C. Okay, so I'm going to plug in the cosine. So it becomes 1 over cosine of x. And then I'm going to chain rule the top limit. The derivative of cosine is a negative sine. And then if you want to simplify this, sine over cosine's tangent. So this becomes a negative tangent of x. Part D. So when we look at part D, we see that our x is on the bottom. So I need to flip the integral and make it a negative. Okay. Like that. And then I'm going to take the derivative of the integral. So when I take the derivative of the integral, I'm going to plug in the top limit. And I'm going to chain rule the top limit, just 1. So remember, properties of integrals. When I flip it, I'm going to change the sign. Part E. When I do part E, I'm going to plug in the x squared. So I get cosine squared to the third power. It's a power to a power, so we're going to multiply the exponent. So it's cosine of x to the 6th. And then I'm going to chain rule the top limit, which is 2x. And then the last one. We're going to have to flip the limits because my variable is on the bottom. So I'm going to flip the limits. I'm going to make it a negative integral of tangent of x. Bring the 17 on the bottom. Okay, now we're going to plug in our top limit. And then we're going to chain rule the top limit. The derivative of tangent is secant squared. Okay, so that's how we're going to use our second FTC. So hopefully this video helped you with Riemann sums and integrals by geometry. The next lesson we're going to get into heavy functions defined by integrals and using that second FTC. So if you have any questions, feel free to reach out. Thanks. Bye.